In May, in a conference hall in Shanghai, a Huawei executive said her company would ship a phone chip holding 238 million transistors per square millimeter, denser than Intel's 18A, nearly TSMC's 3 nanometer, on equipment 3 generations behind. And there is a second number in her slides, 1.5 microns wide, that engineers found more alarming than that one. Her name is Hu Tingbo. The chip is Kirin 2026, and it goes into the Mate 90 in September. To get there, Huawei had to abandon the rule the entire industry has run on since 1965. Shrink the transistor, everything else follows. That was the instruction, and it was unreasonably generous, because one action bought you 4 things: more transistors in the same area, faster switching, lower cost per transistor, lower power per operation. Watch what happened to those 4. Cost per transistor stopped falling somewhere around the 28 nanometer node, which means the most economically important half of Moore's Law quietly expired more than a decade ago. Power scaling broke even earlier, back when clock speeds flatlined and the industry pivoted to piling on cores. What survives is density alone. You still get more transistors per square millimeter, you just pay more for each one, and they do not switch meaningfully faster than the last batch. So the node race is now fighting over the one gift left, with tools that keep doubling in price. A leading-edge fab runs $20 to $30 billion, according to TSMC's own co-chief operating officer. Standard EUV scanners passed 200 million each. The new High-NA machines run about 400 million. Then, in April, TSMC said it would not use High-NA for mass production until at least 2029. A company with a $56 billion capital budget looked at the most advanced chipmaking tool on Earth and decided the math did not work yet. When the richest customer starts hesitating at the price, the ladder has stopped being a ladder for anyone standing below. For Huawei, it was never about price. In 2019, the Commerce Department put Huawei on the Entity List. In 2020, the rule was extended to any chip made anywhere using American tools, which is effectively all of them. The Netherlands stopped licensing ASML's EUV systems to China. SMIC, the Shanghai foundry that builds Huawei's chips, cannot buy one at 200 million or at any price. So SMIC pushed the older tool past its design limits. Their DUV scanners print with light at 193 nanometers instead of EUV's 13.5. To resolve features finer than that light allows, they use multi-patterning, splitting one pattern across several exposures layered on top of each other, like printing a color photograph 1 ink at a time. It works! SMIC reached a 7 nanometer class node this way, and a teardown this year found their metal pitch actually beats Intel's 18A, while running about 38% behind on density. That is a real achievement, and also a treadmill. Every added exposure multiplies cost, cycle time, and the number of ways a wafer can die. There is a ceiling, and SMIC can see it from where they stand, which is when Huawei's engineers stopped asking how to shrink the transistor. Pull up a die shot of any modern processor, the kind of photograph where the copper wiring layers look like stacked street grids. The transistors are not the slow part of that picture. Picture it as a city from above. The transistors are buildings, hundreds of billions of them. The wiring is the road network, stacked across more than 20 layers of copper. A transistor switches in picoseconds. The signal it produces still has to drive down a copper road that can be millimeters long. Copper roads fight back 2 ways. They resist the current, like a narrow pipe throttling water, and they hold charge along their length, so every signal has to fill the wire before it arrives. Resistance times capacitance, RC delay. The longer the wire, the worse both terms get, and they get worse faster than the transistors get better. That is why the clock speed on your laptop has barely moved in 15 years. We did not run out of transistor speed. We ran out of patience with the wires. Look at what the industry has been spending to fight this. Cobalt and ruthenium liner experiments to cut wire resistance. Backside power delivery, which moves the power rails to the underside of the wafer just to free routing space on top. Those are billion-dollar programs whose entire purpose is buying back headroom that shrinking keeps taking away. A thinner copper wire has a smaller cross-section, so higher resistance. The interconnect penalty grows every single time the transistor gets smaller. Huawei's engineers drew the conclusion the rest of the industry mostly accepts in private. If the interconnect is the binding constraint, shrinking the transistor is optimizing the wrong variable. There is a number that makes this concrete, and Huawei leads their paper with it. In a modern computing system, the majority of energy consumed goes into moving data rather than computing on it. Not the arithmetic, the commute. Every one of those hundreds of billions of transistors spends most of its energy budget acting as a courier, charging up a copper wire so a value can arrive somewhere else on the die. You are paying for a calculator and funding a postal service, which means the entire industry has been optimizing the cheap half of the problem for about 15 years. If distance is the enemy, attack distance. Not by shrinking the city, by folding it. They call the framework Tao Law, written with the Greek letter Tau and known internally as Her's Law, after Hu Tingbo. Tau is the symbol engineers use for time constants. That is the whole argument. The metric to optimize is not area, it is time. The engineering is called logic folding. Take a sheet of paper covered in writing. A word at the top left is far from a word at the bottom right. Fold the paper once, and those two words are separated by the thickness of the page. Now do that to a processor. Instead of laying every logic gate on one plane, you distribute the gates along the critical timing paths across two stacked wafer layers and connect them vertically. A signal that traveled hundreds of microns sideways now travels a few microns straight down. Sit with that ratio for a second, because it is the entire economic argument. Sideways across a die, you might cross 500 microns. Vertically through a bonded interface, you cross something closer to 2 orders of magnitude. And RC delay does not scale politely with length, it punishes it. Because both the resistance and the capacitance grow together as the wire gets longer. Cut the distance by 100, and you are not saving 100-fold on delay. You are collapsing a term that was compounding against you. That is why Huawei can claim a density gain and an efficiency gain from the same change. They are not two separate wins. They are the same shortened wire counted twice. Watch the difference between this and what AMD already sells in your gaming PC. AMD's 3D V-Cache stacks a finished memory die on a finished logic die. Two complete chips bonded. Huawei's chairman Xu Zhijun drew the line bluntly, saying folding means folding one sheet of paper, while stacking means putting two separate sheets on top of each other. Logic folding partitions the logic itself, cell by cell, before the layout is finalized. Nobody has shipped that in a consumer product. Which raises the obvious problem, and it is the reason nobody has. Splitting a processor's timing paths across two wafers means your design software has to understand a chip that exists in 3 dimensions. Every timing tool, every placement algorithm, every verification pass in commercial chip design assumes a plane. Cadence and Synopsys build for a plane, and Huawei cannot legally buy the latest versions of either. So the folding architecture required a design tool chain that did not exist in a country cut off from the 2 companies that make them. Peking University built an EDA tool specifically for logic folding designs, and it went public this year. Read that as the tell. You do not build a design tool chain for a slide. There are 2 more numbers coming, and the second one is the reason engineers stopped talking about density and started talking about heat. Stay with me for that, because it is where this stops being a story about a phone. Now the numbers, from Huawei's own paper, and watch the shape of the curve rather than the headline figure. 238 million transistors per square millimeter, up from 155 on last year's Kirin 9030 Pro. 53.5% in a single generation on the same manufacturing node. The previous jump, 126 to 155, took 3 years. Peak clock reaches 3.1 GHz, up 12.7%. Performance core efficiency improves 41%. If those hold, they are the most interesting numbers out of a Chinese fab in a decade. Now I have to take some of that back. Points 1 plus 2 collapsed per audit. Start with the words on the slide. Huawei's 2031 target is 1.4 nanometer equivalent density, and equivalent is doing enormous work in that sentence. Node names stopped describing physical measurements years ago. They are labels for a density class. Huawei is not claiming a 1.4 nanometer lithography process. They are claiming architecture plus vertical integration reaches a density that a 1.4 nanometer process would otherwise deliver. Analyst William Keating noted that even if Huawei hits 2031, it arrives roughly 3 years after TSMC's A14 node is already in volume production. And every performance figure I just read you is first party, measured by Huawei, published by Huawei in a preprint on ChinaKiv. No independent teardown exists because the phone has not shipped. That gap matters most on yield, and wafer-to-wafer bonding makes yield brutal. Bond 2 full wafers and a dead die on the top layer kills the good die underneath it. At 90% good die per wafer, the bonded pair lands near 81% before a single bonding defect. Huawei's paper acknowledges this and states that yield has to approach 100% through redundancy designed into the chip. That is a requirement they have written down, not a result they have reported. Then there is the number I promised you at the start, 1.5 microns. The hybrid bonding pitch on Kirin 2026, meaning the spacing between the copper contacts joining the 2 wafer layers, coverage called it a world first, 6 times finer than anything in production. It is not. Sony has been shipping 1 micron pitch hybrid bonding in image sensors. TSMC's SOIC platform sits around 6 microns with a published roadmap to 4.5 by 2029. AMD's 3D V-Cache is near 9, so the pitch is not the record. What matters is a ratio almost nobody outside the industry discusses. Huawei's paper says the bonding pitch has to stay within about 3 times the top metal layer pitch for cell-level folding to work at all. Kirin 2026's top metal pitch is around 720 nanometers, putting the ratio near 2. Under 3, a cross-layer connection behaves like just another metal layer, and the seam stops mattering to the design tools. Over 3, routing overhead at the interface eats the gains. That is the real claim, not the finest pitch on Earth. A pitch fine enough, relative to the wiring above it, that 2 wafers behave like 1. Sony's 1 micron bonds carry pixels. Huawei is running a phone's critical timing paths through theirs. Which brings us to the wall. Memory chips run cool, which is why the industry stacked memory first. Logic does not run cool. Logic switches billions of times a second, and every switch leaks heat. Stack logic on logic, and the bottom layer's heat has nowhere to go, because the thing above it is also generating heat. Huawei's first target is not a data center with liquid cooling and dedicated air handling. It is a phone. A slab of aluminum, a graphite sheet, and your hand. Huawei's V2 paper does disclose a thermal solution, which is more than most coverage mentioned. CVD diamond heat spreading layers on the top and bottom of the package, with micron-scale liquid cooling channels cut into the middle, carrying fluorinated coolant vertically between the layers and then laterally across the top diamond plate. They put the supported power density near 300 watts per square centimeter, roughly 3 times conventional. Read that description again and ask what it sounds like. Diamond films and internal coolant channels sound like a data center answer, which may be exactly what they are, since the same paper puts logic folding into the Ascend 990 AI chip by 2030. And there is a constraint on a phone that no cooling system solves. A server chip can run at 90 degrees inside a rack and nobody complains. A phone is held. Skin temperature limits mean the outside of that chassis has to stay somewhere around 43 degrees, which caps total sustained power at a handful of watts, regardless of how cleverly you move heat inside the package. Diamond spreading buys you conduction. It does not buy you a place to put the heat once it reaches the aluminum. Whether that stack shrinks into a handset at consumer yields and consumer prices is unresolved. Huawei's own paper calls for industry-wide collaboration on tool chains and standards, which is not how you describe a solved problem. The cost question cuts against the whole framing too. Moore's Law delivered performance and lower cost together. Logic folding does not. Every stacked wafer means another full round of lithography, deposition, and polishing, so equipment and material consumption roughly doubles. You are buying performance with money, which is precisely the trade the industry has spent a decade trying to escape. And Huawei is not alone on this road. TSMC has SOIC, Intel has Foveros, Samsung has X-Cube. NVIDIA's Jensen Huang was asked about Tao Law directly, called the approach sound, and said TSMC's decade of work in stacking means it poses no threat to TSMC. He might be right. That is not the same as the approach being wrong, because the strategic argument underneath this has nothing to do with whether Huawei beats TSMC to a node. Huawei's roadmap runs logic folding into the Ascend 990 by 2030 and claims a 100-fold increase in system integration by 2035. Huawei's chairman has publicly thanked the United States for the export restrictions, saying they supercharged China's domestic semiconductor industry, which is either a very good line or a very honest one. What China is attempting is not catching up inside a race whose rules were written in Veldhoven and Hsinchu. It is arguing the finish line was drawn in the wrong place. So where does it actually sit in July 2026? The density number is real, measured, published, and unverified by anyone outside Huawei. The 1.4 nanometer figure is a density equivalence on a 5-year horizon, with a competitor already ahead of it. The thermal solution exists on paper and has never been proven in a device you can hold. The Mate 90 ships in September. The first independent teardown is roughly 8 weeks behind that. That teardown is the thing to watch. Not the keynote, not the paper, the die shot. And it settles a question that only has 2 answers. Either logic folding is a genuine redirection of chip design, one the incumbents were too comfortable to take seriously, and the sanctions produced the exact capability they were written to prevent, or it is an expensive workaround with favorable first-party numbers, one that collapses the moment that diamond cooling stack meets a phone chassis and a consumer price. Every fact in this video fits both. Pick one in the comments, because September is going to prove somebody wrong, and I want to know where you landed before the die shot lands. Subscribe and you will get that teardown breakdown the week the Mate 90 is on a bench.